Okay, hello everyone and welcome back to your YouTube channel. And today I have a very interesting video for you, okay? Because if you are following this series of videos, you realize that I am spending here a couple videos related with DIgSILENT PowerFactory, okay? I would like to make clear this is not a training about DIgSILENT PowerFactory. This is just a basic illustration for my master students, and it's a very basic explanation. What I'm trying to say is this is not a formal course or training about DIgSILENT PowerFactory. This is only to teach you the basic elements that you need to learn in order to solve some examples, practical examples of the course Advanced Power System, okay? And that is the idea behind this video. The idea is that I will be running some calculations and then also some modeling and finally some simulation. And the idea is that you will be able to replicate those experiments at home using the DIgSILENT PowerFactory version 2021 Service Pack number 1, the version that is the most recent version that is available at the moment, okay? Well, the idea here is to create a test system, a very basic test system from scratch. That means that you must be able to replicate this study case later, and you will be able to perform the simulations, okay? Also, this example is related with transient stability, okay? At the very beginning, in this video, we will just create the system, and I will show you how to run a load flow, okay? That will be basically this basic video here, creating the test system. The test system will be created from scratch using the DIgSILENT PowerFactory. You will put all the objects, all the data, and then at the very end of this video, we will run a load flow. What I'm trying to say is we will calculate the basic steady state conditions, and from there we will move for the next videos, okay? The idea is that my students will be familiar with the use of the tool, okay? It's very important for you, okay? And let me discuss a bit about the test system that we are creating today, okay? In this video, we are creating this extremely simple example. I believe you are familiar with this, okay? If you are following my course about advanced power system or transient stability, dynamic processes, I mean, several courses I use this example. And also this example is not, it's basically present in every single power system analysis book, okay? If you go to Condor, if you go to, for instance, Paul Anderson, you will find this very basic system, okay? This is the system that you will find in many books. There is a synchronous generator over here connected. If you look on the left-hand side, we have this generator. The rate capacity is 100 MVA, power factor, nominal power factor 0.8. We have 11 kV, the rate voltage of this generator, okay? We have a bus bar. The bus bar is called LV, or low voltage. Then we are going to this step-up transformer, and this is a step-up transformer reaching this bus bar over here that we call HV. HV is basically short for high voltage, okay? This transformer, as you can see, there is 11 kV on this side. There is 232 kV on this high side, okay? On the voltage, high voltage bus bar. Then we have two identical transmission lines. You can see here line number 1 on the top And then we have this small line here again at the bottom. Both of them, they are identical, 0.15 or 0.15. This is the per unit value of the reactance in this transmission line, okay? Then we have a bus bar, and that bus bar, we will say that is very strong, that is an ideal connection to a very big power system. That is what we call the infinity bus bar, okay? What I'm telling you is this connection over here, this is defined by the infinity bus bar, is 232 kV. There are some additional data here. If we go here below the figure, you can see the synchronous generator G, this unit here, has an inertia constant of 8.45 megajoule per MVA, okay? And transient reactance, okay, it's already defined here in the figure, but let's say again, the transient reactance, it's equal 0.2 per unit. And the synchronous generator is connected by a pure reactive transmission system to provide power to an infinity bus bar. In single words, what I am trying to say with this final paragraph here is that this system has no resistance, okay? This is pure reactive. That means subtransient reactance here. We have the transformer reactance here and two transmission lines, and the model is the most basic. They are not resistant, only the reactive component, okay? Well, now what we need to do is to create this system, inside the DIgSILENT PowerFactory. And to do so, what I will do is I will start PowerFactory, and from there we will start to work, okay? Okay, right now we are here. We are inside the DIgSILENT PowerFactory. As you can see, this is the welcome window over here where PowerFactory is showing you the examples, okay? I highly suggest to all my students and everyone watching my videos, please be familiar with those examples over here. They are very beautiful and useful examples. PowerFactory make a strong effort and provide to you quite good documentation, okay? Also, there are videos. If you are not familiar with those examples, what you need to do is very simple. Here, for instance, this is the low voltage distribution network, and there are several examples. There is a base model, then they talk about the load flow at the low voltage side, using probabilistic load flow. Then you have here some activity for feeders load scaling, and so on, okay? As you can see, there are videos here, and what you need to do is just press the button and you will get the video, okay? And also you can import the file, you can import the project just by pressing this button. It's extremely simple. You press here and it will import the project and activate the project for you, ready to go, okay? They are very interesting examples over here. Many people write me emails, send me emails, and ask me for the 9-bus test system. The 9-bus test system is already created and is inside the DIgSILENT PowerFactory, okay? It's an example. PowerFactory people, they developed this model and include many versions ago. This is the PM Anderson, the classical 9-bus system, including the book. Here, this is the IEEE 14 bus bar. This is another test system that is very well known for scientists. This is the IEEE 39 bus system. This is a really simple model, but is very interesting for analyzing transient stability. And PowerFactory people include here. We have a test feeder. This is for distribution. This is the classical IEEE 13 nodes test feeder. Here we have something for the Rowe-Billington book, okay? This is the Rowe-Billington test system. This is the 2-bus system. Also, there is an example for a subsynchronous resonance, and here we have the test system coming from Sigre, and there is one more for resonance studies, okay? Well, but this time to close here, I don't want to go for I don't want to work with example because I will create my own example, okay? The first step here is we need to create a new system. Some of you probably, before I start to create the system, some of you probably will complain, come on, the fonts are so small, I cannot see the thing, and so on. At this moment, I am recording this video at 4K, okay? This video is 4K quality. That means that this video look like the letters are extremely small, but if you zoom in, or if you have a big screen, you will get a better view rather than increasing the font, okay? When I increase the font, you lose some quality because I need to use a low definition, but right now I have the possibility of recording those videos to 4K at 4K, and you have the best of the best quality to watch those videos, okay? Well, let's start the example, okay? What I will do is going to here to the top file, and I will create a new project, okay? File, new project, and I will call this the test system, okay? I will call this test system. Test system, okay? Here you can include some information, okay? You can include a description, okay? This is a single generator connected to a infinitive busbar, okay? Connected to infinitive busbar, okay? Because the idea of this example is that we will use for transient stability later, okay? My idea is we will start with this very basic system, and from there you will see that we will use later for a very simple example about equal area criteria, okay? What I'm talking to you is that we already solved this test system using classical equal area criterion, and we can get the results about the transient stability analysis. But here in PowerFactory, I will show you that we can use this system for that same purpose, okay? Okay, now we need to put here some name for the network. I will call this the Power Network, okay? This is my personal favorite name, Power Network. And then we need to put here the owner. You can put your name. I will put mine here, Professor Francisco Gonzalez-Longatt, okay? Also, if you want to add any description, you can do it here. I will just keep my name here just for the track, and also I will use this name, okay? Right now, when you press here, okay, you can see that a new network element will appear basically with the name Power Network, okay? Press OK. PowerFactory is creating the object. You can see here at the top there is a tab, and inside that tab you can see the name, and this is basically Power Network, okay? Now what I will do is we need to create the power system. We were talking about a very basic power system. They are basically 3 bus bars over there, the low voltage side, the high voltage side, and the infinity bus bar, okay? What I will do is the following. If you are familiar with DIgSILENT PowerFactory, DIgSILENT PowerFactory is basically a software that is for utilities, okay? When we are working inside the utility, probably time to time we need to have the full representation of a substation, and you must remember that there are different type of bus bar scheme inside the substation. If you go here, you can see that there is a label that say bus bar systems, because that is the objects that we use when we want the full representation of the bus bar systems, okay? Here we can go and select, for instance, if we want to use a single bus bar, or we can go further. For instance, this one here, this is 1.5 bus bar. That is a typical substation bus bar system, okay? Some countries, they use this 1.5 bus system for transmission levels. specifically for 400 kV or even higher, okay? You must remember something from substation, that those bus bar systems, they are different because they offer different reliability configurations, okay? I will not go there. I will use a very simple bus bar, and to be honest, I will use the element that we call the terminal, okay? What I will do is I will take one of these, click here, and then go back here to this element network here, and click, and we have the terminal one, okay? In order to replicate the same structure that I have in the presentation, I will rotate this. To rotate this, what I will do is rotate in the clockwise, okay? Right now it's in this way, and because we want to have two more of this, let me copy and then paste. You can use copy and paste inside PowerFactory. Right now you can paste here and you can paste here, okay? We will call this the low voltage. Remember, this is the low voltage bus bar, and the low voltage bus bar, if you go to the single line diagram, is 11 kV rate voltage, okay? Line to line, 11 kV. And this is the low voltage, and this is 11 kV line to line. Then we will go to the high voltage side of the transformer, and this is the bus bar that we call the HV. And you must remember, from the single line diagram, you can go to the presentation 232, okay? Simple. Then we have here what we call here the infinity bus, okay? Infinity bus, okay? And the nominal voltage again is 232 kV line to line, perfect. And we have here the 3 bus bar, okay? Let me zoom in here. We can zoom in here because I want my student to have a better look of the system. Everything is in gray right now, gray color. The 3 bus bar are in gray color because, as you must remember, those elements, they are not connected to energy sources, okay? And that is the reason that we have over there the gray color. What I will do now is I will include 2 transmission lines. Let me go here to the left panel, and I will go for the classical overhead transmission lines, and the symbol is here, okay? There is a section for lines, cables, and series impedance. I will take the line. I need 2 lines, one from here to the infinity bus bar, one more here, and let me call this one the line 1. Line 1. And the second one is the line 2, okay? And right now we have 2 transmission lines, but just the drawing and the basic data that is coming by default at the element, okay? Then we need a transformer. Let me put here a transformer. We are using a 2-winding transformer, very simple. We connect here at the low voltage side, then on the high voltage side, voila, we have a transformer. Let me change the name to follow the names. And this transformer, the name here is T. Finally, we need 2 more elements. Those are shunt elements. You can see here we have the generator. We can go to the left panel, and there is a section for generators and loads. And the first one that you can find at the extreme left side is the synchronous generator. And voila, now we have a synchronous generator. The synchronous generator is connected to the low voltage bus bar. And as you can see, everything suddenly become a black color. And it's becoming black color because right now we have an element that it can be able to provide electricity, energy to this system, okay? And let me change the name, double click here, and we are inside the element synchronous machine, and I will use G because that is the name in the presentation, okay? We have the generator G over there. Next step, we need a very specific element to represent the infinity bus bar, okay? I saw many videos on internet and they use a external grid to represent the infinity busbar, okay? It's an option, to be honest, it's an option, but it will require some configuration, okay? What I'm trying to say is the external grid is a concept that we use to create a model of a large portion of the electrical power system, but keeping some elements, modern elements regarding that very large network, okay? What I'm telling you is that, for instance, for electromechanical processes, that system, that external grid, there is a possibility of including, for instance, inertia, okay? It's not good idea to use the external grid as a model for the infinity busbar, okay? I highly suggest to my students and everyone watching this video that you use the voltage source, okay? Because the voltage source is the best way to represent infinity busbar, okay? What is the reason? Okay, let me change the name here. Infinity busbar, okay? I will call infinitive in short bus, okay? And what you can see over here is I prefer this element because in this element you have full control regarding the impedance that is in series with the voltage source. What I'm telling you is this element, the element VAC, is basically a Thevenin model where you have some impedance. You can see here, this is the positive impedance, zero impedance, negative impedance, and so on. Negative sequence, of course, and zero sequence impedance. And this control allow me to include zero over here in all those elements, okay? Because when we are simulating an infinity busbar is a busbar with constant frequency, constant voltage, and constant angle. And as a consequence, to replicate that, the most simple way, the fastest way to do it inside PowerFactory is using this element, the element voltage AC, voltage source AC, and keeping zero all those impedance make the concept real, okay? I'm not telling you that you cannot do that with the external grid. Of course you can do it, but you need to do some assumptions and changes, and time to time, if you are not expert, you can make mistake, okay? This is the best way that I teach my students in order that they avoid mistake, okay? It's very important that you be familiar with every single model that you are using. What is the model internally? There is a circuit model. There are equations. Have a look on those models. Have a look about the assumption of those models. You need to be sure about that. Okay. Okay. Right now we create the single line diagram, but we are not able to run any calculation. And the reason is because this is a graphic. This is a graphic object, but there is not electrical data related to the models. For instance, if we double click here at the transmission line, there is no type for this transmission line, okay? We need to define the resistance, the reactance, capacitive and inductive reactance of this transmission line, and so many other things. And also here in this transformer, for instance, also there is not a type. Remember that the object type is where we define, for instance, the nameplate data. The rate capacity, MVA, the transformer ratio, the short circuit impedance, and so on, okay? Be careful, be careful. At this moment, we cannot run any simulation, but we have a beautiful single line diagram, okay? What is the next step? The next step is, after we create this model, we need to put data. And to put data, the best way to do this is basically having the correct values that we need to put here, okay? And for that reason, I need to come back to the presentation, okay? Let's go back to the presentation. And right now we are here at the presentation, okay? And in this slide, in particular in this slide, you can see that, okay, we have the generator, transformer, we have here the transmission lines and the infinity busbar, okay? The first thing that you need to understand is that inside PowerFactory, you need to use real units. I mean, Power Factory, for transmission lines, you need to use the ohms, the real ohms that we need to put for the resistance and the reactance, okay? And if you remember, the original data that was provided in this problem, it was in per unit. For that reason, we need to run some calculations, very basic calculations, in order to obtain the ohms, okay, the real reactance of this transmission line. What I'm telling you is that this reactance is 0.15 per unit. But in this case, we are making a couple of assumptions. The first assumption, we will use the nominal power, apparent power of this synchronous generator as a base. What I'm telling you is, I will say that those per unit values are represented in this base of 100 MVA. That is the first step. Second, I will assume a voltage base for this transmission system that is 232 kV here at the transmission side. What I'm telling you, this is the base voltage, 232, using the transformer ratio, because this is a 3-phase 2-winding transformer. The base voltage is 11 kV on this side, okay? That is extremely simple. Voltage base here is the base voltage in this side. Let me use here in this side we are using 232, and using the transformer ratio we can transform the base, and on the low voltage side we have an area, and this area is for 11 kV voltage base, okay? That is basically what I am telling you here, okay? What is the next step? Well, we know the bases. Now we know the apparent power. We know the voltage. And I need the reactance, inductive reactance of this transmission line. I need those values in real units, ohms, okay? And to be honest, this is extremely simple, because all my students, they are extremely knowledgeable regarding per unit values. And what you need to do is, okay, calculate the impedance, the base impedance. And the base impedance is extremely simple. There is an equation, a square value for the voltage base divided by the apparent power base. Voltage base, I already say 232. You can see over there, 232. The square value of this 232 kV divided by the apparent power base, in this case is 100 MVA, okay? When we put the number together, you can use calculator, you can use MATLAB, any mathematic tool that you want to use. The impedance base, in this case, is 538.24 ohms, okay? That is the impedance base. To obtain the real inductive reactance of those transmission lines, the procedure is extremely simple, because what you need to do is multiply 0.15 per unit, multiply by the impedance base 538.32. That is extremely simple. And the result, simple, 80.736 ohms. And that is the real inductive reactance that I need to put inside the DIgSILENT PowerFactory, okay? I will repeat, it's extremely simple. What you need to do is multiply the per unit value by the impedance base, and from there you will obtain the real impedance, real reactance in this case, and the value is here, okay? Well, let's go to PowerFactory and start to put this data inside PowerFactory, okay? What I will go back again to PowerFactory. Let's do that. Well, now we are here inside PowerFactory, and I will do this extremely fast because my students, they already know how to do this. And it's very simple, okay? Double click at the transmission line, and we go here to this section that say type, and we need to create a new project type. In this case, there are different types, object types that we can apply to the transmission line element. However, I will go for a very simple, very straightforward, the line type. Okay, let's select this one, and I will create a new project type, the line type. Okay, right now it's asking for the type. I will say this is the 232 kV line. Okay, just to present the name. Then I will complete the data, 232. I will not change this rate current. Later we can change in order to visualize. If we want to visualize overload in a proper way, we can take care of this. Okay, the system is 50 Hertz, and what I will do right now is let me put over here the value 80.736. Okay. No, sorry, this is the resistance, it's not here, sorry. Here is the reactance, and we will use 80.736, okay? I will tell you again, what you need to do is include the name, then the rate voltage, in this case 232, then go here to the reactance, and we will say, we will include here the reactance, in this case is 80.736, okay? Some of you are wondering, okay, you are using ohms per kilometers. Yes, PowerFactory asks you for the type, the ohm per kilometers, defining the reactance per length unit. That is a requirement of PowerFactory. And then inside the object element, we can include the total length, okay? In this case, we already know that the total inductive reactance is 18.736 ohms. What I am doing is including that number as the ohm per kilometers, and then I will say this is a transmission line of 1 kilometer. If we multiply by 1 kilometer, kilometer unit disappear, the length unit disappear, and we obtain the total 80.736 ohm, okay? Something that I will do here, this is something to make clear that this is an overhead transmission line, okay? This is an overhead transmission line, and now I will say, okay. And if you look over here, automatically, when I complete the data of this type, already PowerFactory is showing you the positive sequence. Let's go for the positive sequence reactance. And you can see the value is 80.736 ohms because the total length is 1 kilometer, okay? Well, what we need to do now is say okay. And as you can see over here, this transmission line has a type, okay? And the type is line time 232 kV. I need to add that type to this transmission line because both of them, they are equal, okay? I say to you that the inductive reactance of those transmission lines, they are identical. And to do so, what I will do is just double click, okay? Right now, we are inside the element transmission line, and the name is line 2. And what I will do is go here to type, and I will select a type because we already create a type. That is the type transmission line. Let's select here. PowerFactory open for you directly in the proper location inside the local library, and specifically inside the folder equipment type library. You can see the type that I already created. This is the type line 232 kV. I will select, voila, you get the data. In this case, you can see that the positive reactance is a 0.736 ohms, okay? Because the total length of this line is 1 kilometer, okay? Now we are done with the transmission line, okay? The transmission line was extremely simple. I think you will find also the transformer extremely simple, okay? Let me show you here. Both transmission lines, they have the same type. and it is because both transmission lines are identical, okay? Next step, double click at the transformer. Again, it's you can see over here the type is missing in this transformer. It's very important that we complete that data. And right now what I will do is select type, okay? And now I will select here new project type, okay? When I select new project type, I am creating a type for this new object, okay? And I will say this is the type. If you remember, we are using 100 MVA, okay? We are using 100 MVA, and this is the transformer going from 11 to 232 kV, okay? This is the transformer. Okay, be careful. Remember that it's lower letter K by kilo, and we use capital letter V because V is the voltage unit, volts, okay? In this case, we are using a 100 MVA transformer, okay? This is a three-phase transformer, 100 MVA, 50 Hertz, because we are working here with a 50 Hertz transformer. And the high voltage side is already known, 232 kV, extremely simple. And the low voltage side is connected to the generator, 11 kV, okay? Now we have complete this data here, but we need a very important data, and that is the positive sequence impedance, okay? If you remember, if you go back to the presentation, you can look the data at the presentation, and the transformer reactance, it was 0.2, okay? 0.2 is the reactance, inductive reactance of this transformer, okay? The inductive reactance is identical to the short circuit voltage. In this case, is in percentage over here. We can use 20% to represent 0.2 per unit, okay? That is one way to do it. Another way is going here and use the selection for the different input data. And I am including here reactance in per unit and resistance in per unit. And automatically you can complete the data in per unit to follow the data provided to you, 0.2 per unit. In this case, well, we already finished the data with the transformer. It's extremely simple. And let's press here OK, and here OK. Right now we have here the transformer. You can see the name is T, and the line below the name is indicating the type. That is the configuration for showing the data at the elements. This is the name of this element. This is T, the transformer T, and here below you can see the type, okay? Next step, and finally, we are reaching the synchronous generator. Synchronous generator, a lovely machine, but is probably one of the most beautiful components inside the power system, but also one of the most complex, okay? If we double click this machine, again, there is missing data over there. The most important missing data here is referred to the type, okay? In this case, the type of this machine is missing, and I will follow the same procedure, okay? I will say new project type, and in this case, I will call this type G, okay? And I will say this machine is 100 MVA, and you must remember from the example, from the presentation, you must remember that this machine is 11 kV, okay? 11 kV, and also the power factor is 0.8, and it's already there, okay? As you can see over there, we are completing the data for the rate apparent power, the rate voltage, the rate power factor, okay? That is the most important data at this moment. But also we have another data that we can complete, and that is the inertia and this transient reactance, okay? I will not do so right now because at this moment I'm not running time domain simulation, okay? Keep in mind that we didn't put right now the inertia constant, and we didn't change the data of the transient reactance, okay? We will do that here. We will do that here at the simulation RMS tab, okay? We will do that later. Let's just press here, okay? And right now, this synchronous machine has here a type, and this is the type representing the synchronous generator, okay? Now, as you can see, again, we have here on the top, we have the name of this object. This is the generator G. And as you can see, there is a type, and this is the type G that we defined before, okay? Well, to be honest, this system is almost ready to go, to be honest. This system is almost ready to go. There are only a couple things that we can do at this moment, okay? There are a couple things that we can do at this moment in order to verify if this system is properly working, okay? I highly suggest my students, when you finish completing the data, it's very important that you be able to identify and see if all the data is properly working and if the system is able to run the simulation. And the most basic simulation that you can run in this system is the load flow, okay? I highly suggest every time that you finish creating your system, the best way to assess if the basic data is properly working is just running a static analysis, is running a load flow and checking your results with the theory, okay? It's very important that you understand that the software is the practical aspect, but without theory you cannot be sure, okay? What I will do now is I will come back to the presentation. I will go back to the presentation, and from there, we will see some data that we need in order to run the load flow. And let's go back to the presentation. Okay, right now we are here at the presentation, and there is some very important data, okay? And in this case, the important data that I need to run the load flow, the basic load flow for checking some results, it's basically this generator is producing some active power, okay? In this case, this generator is producing 0.6 per unit, okay? If you remember, the base power in this case is 100 MVA. As a consequence, that generator, synchronous generator, is dispatching 60 megawatts, okay? 60 megawatts coming from the synchronous generator, going through to the step-up transformer T, then is divided between the two transmission line by finally reaching the infinity busbar, okay? And the other important component here is that you must know that the voltage of the infinity busbar is 1 per unit, okay? What I will do now is I will set up the operational conditions, the operating conditions in this test case, okay? What I will do now is going back to PowerFactory. Inside PowerFactory, I will set up those values. First, I need to set up the active power dispatch from this generator, and then I will set up the voltage at the steady state voltage at the infinity bus bar, okay? And right now, let's go to PowerFactory and do that. Well, here we are. Right now, we are at the test system. And the first step is we want to set this generator, and this generator is set to provide 60 megawatts, produce 60 megawatts, okay? And something that you must understand, if we double click here, we access the elements synchronous machine, and in this case, I will go to the load flow, okay? Inside the load flow tab, there is here two very important sections, okay? One section here is defining the dispatch, okay? When I say the dispatch is this generator has a nameplate or a rate power of 100 MVA, okay? But that is not the power that is produced by this generator. This generator has the possibility of producing different level of power, active power and reactive power, and the maximum, the rate power of this machine is 100 MVA. In this case, we will use here 60, we will say here 60 megawatts, okay? In this case, this generation unit will be dispatching 60 megawatt. You can see over here, the actual dispatch is 60 megawatts. And you can see over there, the reactive power is 0, okay? That is presented here. You can see 0 MVR. And in this case, of course, the power factor is 1, okay? And this is the data that we are presenting because this generator is working at constant reactive power, okay? There are different controllers, local controllers that we can apply to this synchronous generator. You must remember that from your classes of load flow, okay? All my students, they took an amazing module about power system, basic power system analysis, and they know about load flow, okay? When I say constant Q, constant reactive power, to be honest, we are modeling the synchronous machine as a classical PQ busbar. And the only difference is that in this case, we are talking about a PQ busbar, but it's going into the busbar. I mean, it's active direction, it's production direction, okay? And there are another local controllers here. You can use constant V, and that is the classical PV bus bar that you saw in your classes about load flow, okay? And also there are more sophisticated controllers. I will not cover that here because that is not my priority here. I will say constant Q here. And in this case, the generator will be generating, it will be producing 0 MVR, okay? And right now, what I will do is, okay, and this machine is ready to dispatch 60 megawatt and 0 MVR, okay? And I will go now to the bus bar, infinity bus bar, and I will check the voltage, okay? If you remember from the presentation, we say that the voltage at the infinity bus bar is magnitude 1 per unit. And that value is located here. What I'm telling you is that this infinity bus bar is already set for 1 per unit, and nobody say anything about the angle, but I will assume, as usual, that the infinity bus bar can be defined as the reference bus bar. And because this is the reference bus bar, I will assume that the voltage angle is 0, okay? That is a classical assumption, but be careful in the exam paper, okay? Sometimes a number different to 0 can appear in the exam paper, and sometimes the student forget that, okay? Be careful with that. Please pay attention to every single number, okay? In a real power system, finding the bus bar with 0 degrees sometimes is difficult or probably impossible, okay? Real power systems, there is another kind of situations. I will not cover this here because this is not the video for that, okay? But right now in front of you, you complete the data and it is time to run a load flow. And to run a load flow, there are many ways to do it. You can go here to the top, to the tool bus bar, and you can follow, you can find here load flow, and you can say load flow, okay? That is one option. I call that the elegant way. People that they know how to move between menus inside the DIgSILENT PowerFactory. That indicates some education and some skills using the software. And time to time, people prefer the other way, the easy way. There are people that they call the lazy way. Okay, I will not go there. That is not my problem. There is an icon here, and if PowerFactory, if DIgSILENT put the icon over there, it's because people use it. Okay, I will not call people lazy. But in this icon, you press here, and the command load flow opens for you. And as you can see, this is the command load flow calculation. You can see here at the top, at the title, COMLDF. And that is the command load flow, okay? This is the command that we use for a steady state analysis, and I will not change configurations here, okay? Because I want to run the classical AC load flow. In this case, we are using positive sequence for the model of this transmission system. There is no problem. That is what I want, positive sequence balance. And I'm not considering any of those options because we don't have tap changers, we don't have reactive power limits. At this moment, I don't want to include any reactive power limits. And also, we don't have voltage controllers, and as a consequence, I will not take in account here or load, okay? What I will do is basically execute, ouch, and we got an error, okay? Let's see what is the error here. That can happen, okay? It's not ideal, nominal differ by, okay. The infinity busbar is 232 kV. And let's see here, okay, that is the problem. I forgot to include the nominal voltage or rate voltage of this AC voltage source. And this is 232 kV, okay? Right now, let me clear again let me clear here the output window. Remember, this area here is the output window. Let me clear the output window. I will say yes. Let's run the load flow again, keeping the default settings. Now we have a load flow. Perfect. And in this case, we have here PowerFactory telling you the reference is the infinity bus bar here on the right hand side. Yes, we know that because we define this as 0. And we have the basic configuration inside PowerFactory. The default configuration is using the classical Newton-Raphson algorithms. And there are 3 iterations. And after 3 iterations, we have here the full load flow, okay? And in this case, when we finish here, we have the load flow, okay? Right now we have, let's see, we have the proper load flow. How do we know that this is properly working, okay? First, let's check the logic. The basic logic here is, here the voltage at the bus bar should be 1 per unit at 0 degree. Perfectly fine. You can see over there 1.0, and in that case you can see 1.0, okay? But the other thing that you need to check here is this network is purely reactive, okay? What I'm telling you is this network over here, there is basically reactance, and as a consequence they are not active power losses, okay? For that reason, all the active power, the 60 megawatts, starting from the synchronous generator at the very left of this single line diagram, 60 megawatts. The 60 megawatts is going through this generator, going through this transformer. You can see 60, and as I told you, this is a transmission system. The 2 inductive reactants, they are identical, and as consequence, you must know that Ohm's law keep working, of course, and the active power is divided between the 2 transmission lines, and in this case, each transmission line is having the half of the total power. If 60 megawatts are coming here, you can see that now we have 30 in this transmission line 1 on the top, and we have here 30 megawatts at the transmission line 2 at the bottom, okay? And of course, you come back here to the bus bar at the infinity bus bar, and 30 plus 30, you can see here 60 megawatts going into the infinity bus bar, okay? Right now there is no reactive power production at the generator, but all the active power coming from here is going there. Okay, that is a very important aspect. Okay, what I will do now is I will change this generator, the controller, the local controller. Okay, and let's do the following. Double click here, going to load flow, then going to constant V. And when I say constant V, you can see that the configuration here changed. And right now you can define the voltage, the set point for the voltage that you want this controller, local controller, to enforce. Because this local controller is enforcing, in this case, constant voltage, and the voltage should be 1 per unit. And what I will do is, right now, I will close the generator, I will run the load flow, let me clear the output window, run the load flow, and voila, you can see over here right now the voltage at the bus bar, LV bus bar, you can see it's 1 per unit. Okay, but right now the synchronous generator is producing reactive power, and the reactive power that is produced here is basically to increase the voltage at the bus bar LV. Okay, however, something that you must understand here is there are some reactive power production here, and then we have a reactive power load flow. Okay, to be precise about how the active and reactive power move, I can suggest that you use some functionalities here inside PowerFactory. PowerFactory, a couple versions ago, they include the possibility of adding some arrows in the single line diagram, and those arrows, they can represent the direction, power flow direction. In fact, you can configure the power that you want to represent with those arrows. Okay, what I will do now is I will go here to layers, and right now what I will do is from layers, remember we press here layers. Okay, layers, we can go here into element details, and right now you can tell to PowerFactory, please now show me the power flow direction. Okay, and at the very beginning what I will do is I will tick here power flow direction, but I will show just the active power. Okay, in this case, when I do that, you can see over here the arrows are coming from the synchronous generator and reaching the infinity bus bar. And the reason for that is basically because this is the device producing active power, and the infinity bus bar is taking that active power. Okay, but then you can do similar experiment, and right now let me click here layers, and let's go to elements detail, and now we want to show the reactive power flow. Okay, what I did is let's go here to the second option is reactive power. We will say okay, and right now let's run the load flow. Okay, and right now you can see over here, okay, this synchronous generator is producing reactive power, but at the same time there are contribution coming from the from this external grid, this infinity bus bar. Okay, what is the reason for that? This generator is providing reactive power to control this voltage, but the reactive power that is produced here is just for local control. And because we have reactive power losses in the transformer and the transmission lines, the reactive power must come from somewhere else, and the only device allowing that reactive power production is the infinity bus bar. Okay, you can see, let me see if we can use the animation. Okay, there are so many students that they love this animation style. I don't like so much, but let me use, because sometimes it's very illustrative. Okay, if we go back to layers and elements details, there is a tick here at the very end of this that say show animation. Okay, when you do that, PowerFactory is doing some small animation for you, and you can see how the arrows are moving. Okay, right now you can see how the arrows are moving, and this is indication. You can see that the reactive power is coming from the infinity bus bar to cope with the reactive power losses in this area, but this generator is producing 5.0 MVR to cope with the voltage regulation here. Okay, and finally, I would like to do something else. Give me a second. Let me change here the configuration at the load flow, and let's use classical active power. Okay, what I am doing here in layers is I will keep the animation, but the arrows will represent now active power. Okay, let me do that. Run the load flow. And we can see over here the active power is coming from the generator 60 and reaching the infinity bus bar. You can see clear over there. Okay, what I will do now is change again the local controller that we have at that synchronous generator. I will do so just to show you. In this case, what I will do is let's do the following. Okay, let's go to load flow tab. And let's come back here to constant Q, okay? Constant reactive power. We are using local controller in this synchronous machine, and the local controller is working as constant reactive power, okay? And I will change here the input mode. I mean, you can define different input modes for this machine. And I will use something quite interesting. I will use here active power and power factor. Okay, and right now I will use 0.8 power factor. Okay, I will select here 0.8 power factor, and from there let me run here my simulation. And as you can see, something interesting is happening here. Okay, right now the machine is producing 60 megawatts, but is also producing 45 MVR. Okay, 45 MVR. The first thing that you must notice is this bus bar, the bus bar LV, is in red color. And the reason that is in red color is because this voltage in per unit, you can see 1.1 per unit. Okay, that is over voltage in this case, steady state over voltage 1.1 per unit. Okay, PowerFactory is telling me in this red color that the voltage is high, but that is because we are producing so much reactive power. And because we are producing so much reactive power, you can see from here they are departing 45 MVR, and from there it's reaching here 32.2 MVR. Okay, what I'm telling you is right now the reactive power flow is changing. The direction of the reactive power flow is changing because we are producing so much reactive power. The voltage here, it will keep it will be 1 per unit, and it's because it's basically dominated by this ideal voltage source. But as you can see, we are increasing the voltage profile. When we inject more reactive power here from this synchronous generator, we are increasing the voltage, and that is the reason for this 1.03. Okay, well, at this moment I would like to stop this presentation, and it is time to close this presentation where we create this basic test system. And we spent here almost 1 hour just creating this basic system and showing you a couple things about load flow, okay, the steady state performance, okay. But right now this test network is working. We tested, we show it. We saw different effects. We show the use of the animation to represent using arrows the power flow directions: active power flow direction, reactive power flow direction. Okay. However, remember, this course is about power system dynamics. Load flow is for kids. Sorry for saying that. Don't be offended. It's just because load flow is something that we do every single day, every single moment. Okay. It's time to go for something deeper, something better. And what we will do in the next video is to calculate initial conditions. Okay, when we are calculating, when we are interested on dynamic processes inside power systems, the first step must be calculating the initial conditions. Okay, but before calculating the initial conditions, we need to reproduce the proper initial conditions that we want for the problem. Okay. And we need to run some setups in this test system, and that is the motive or the reason for the next video. Okay. Well, again, thank you very much for watching this video. If you like it, please subscribe to the YouTube channel and stay in touch. Okay. Thank you very much for watching, and see you at the next video. Thank you. Bye now.